Okay, good morning, everyone. Hope you're well where you are, and thank you very much for joining us this morning. We're going to continue our radio interferometry lecture from 2 weeks ago, moving into some more details about how we do radio interferometric imaging and calibration of those images. So at the end of this lecture, you should have some understanding for how we measure visibilities and then turn them into a dirty image. And you should know how that dirty image can then be cleaned using iterative deconvolution algorithms. And you should understand the various effects that complicate this process. And you should have a basic understanding of the steps that can be taken to calibrate this image to improve it. So before we start, just a small disclaimer that I'm by no means an expert on imaging. My own research uses beamformed observations much more commonly. So I don't really have that much experience doing imaging as such. So I'm sure there are people on the call who have much more experience with it than I do. But the idea of this lecture is to give you kind of a basis in the concepts at least, so that hopefully you can use them in your own imaging. But if you have specific questions about different software and so on, we have experts in the group who I think would be better suited to help you with that. So to recap things a little bit, some important concepts in radio astronomy. The basis of everything is this notion of an aperture of an antenna, which we could think of as the hole through which radio signals are collected. And the beam pattern of that antenna is a Fourier transform of the aperture. And this gives us the diffraction pattern produced by the signals going through that aperture. And this beam pattern tells us how sensitive the antenna is in different directions. If we use a radio interferometer with many different antennas, we don't have a single aperture anymore, right? So instead of that, we use these visibilities, which we define using this equation. And each baseline, meaning each pair of antennas, gives us one measurement of this visibility function. And it's a complex number that we measure. So there's a real part which corresponds to the cosine response, and an imaginary part that corresponds to the sine response. And then we use these visibilities all together basically to simulate a single aperture, which we can then apply a Fourier transform to. Before we do that, we define some UV coordinates, which is a convenient coordinate system projected onto an eastern and a northern direction. And then the basic theorem is the Van Sittert-Zernike theorem, which tells us that the visibilities measured on this UV coordinate system is a Fourier pair with the intensity of the sky as a function of position, which is another name for an image of the sky. So in other words, we can apply a Fourier transform to these visibilities to get an image. And the idea of aperture synthesis is that we can use many baselines, each of which measures a single value of the visibility, and then we can use a two-dimensional Fourier transform to retrieve an image of the sky. So that's the simplest possible explanation for what we do. It's the ideal Fourier relationship where you have a visibility space, do a Fourier transform, and you get an image of the sky. But of course, in reality, the problem is we don't have a visibility measurement for every single combination of U and V. We only have a finite number of baselines, meaning we only have a finite number of samples on the UV plane, and there are always going to be spaces in between those samples. Furthermore, we don't have an infinite distance between antennas, We don't have an infinite baseline, meaning we are only able to sample the UV plane up to a certain distance away from the center, which defines the resolution of the telescope. So this van Sittert-Zernike theorem is really only imperfectly true. And in practice, things look more complicated. It looks more like this picture. So because we have the impartial UV coverage, the top left, we have measurements for some values of U and V. When we do the Fourier transform, we get an image that looks like on the bottom left here, where you have an image of some object, but around it there's a bunch of these artifacts surrounding it, and it's all blurry and you can't quite see what's going on. And that's caused by these missing UV values, which means that there is missing information in the image. Fortunately, we don't have to stick with this dirty image. We can improve it by doing something called deconvolution. To do that, we first calculate what's called the dirty beam of the telescope, which is also called the point spread function, or PSF, of the telescope. And what you can think of this as the image that you would get from the telescope if you were to point at a single point source in the sky. So if you were only to observe a single point of light with nothing else in the sky, that gives you your dirty beam, or PSF. And if we deconvolve this dirty image with that dirty beam, meaning we get rid of all these artifacts, then we can get something that's closer to a true image of the sky. This is called a cleaned image, or true image. So the dirty image that we get from the Fourier transform is the sky brightness convolved with the dirty beam, or the PSF. If you know anything about, for instance, how a digital camera works, it works on the same principle. The image that you get out of the digital camera is a convolution of the actual light that comes into the sensor, convolved with the camera's point spread function. And each camera has a unique point spread function, which determines what the output image is going to look like. So for example, if we have a picture on the sky that looks like Donald Duck here, if we use a point spread function like this, if we convolve it, if that point spread function was a single point, if it was an exact point source, if it didn't have any extent, then we would get back an exact copy of the sky. But because the because the PSF is spread out, then it adds a blurriness to the image that we get out. So in order to get a clean image, we have to remove the effect of this PSF. We have to deconvolve the dirty beam from the dirty image. And we should always be aware in astronomy, we are working with dynamical systems, meaning that the dirty beam can vary with time, position, and frequency, and polarization, which I don't have here. And so we should always be mindful when we make images. We have to correct for this dirty beam across all those 4 different dimensions: time, position, frequency, and polarization. So it can get very complicated very quickly. But to keep things simple, to get the dirty image, we apply a 2-dimensional Fourier transform to the visibilities, right? But Fourier transforms are computationally quite expensive. If you have an n by n image, n pixels by n pixels, the compute time that it takes to do a Fourier transform increases with n squared. So if you have a big image of the sky, very quickly it takes very, very long to do the Fourier transform. So typically, instead of doing that, we use what's called a fast Fourier transform algorithm, or an FFT, which is an optimized algorithm which increases in compute time as n log n. So it makes things significantly faster, especially for big images. The problem is that this FFT requires for the visibilities to be on a regularly spaced grid. So you can't just have a visibility anywhere in UV space. It has to be fit onto a grid. And so we have to resample the visibilities onto a grid, which is called gridding. And because we're moving the UV samples around, that introduces some artifacts into the image. And these artifacts are proportional to the coarseness of the gridding. So if we use a coarse grid, we get lots of artifacts. If we use a finer grid, then there's fewer artifacts. But of course, the finer the grid, the longer it's going to take the FFT. So it's a compromise between computing time and these artifacts. We can also apply different weights to each visibility before the FFT. This is called weighting. So you make some samples on the UV plane count more than others. So for example, if you want long baselines to count more, if you want to emphasize the fine details in your image, then you can give the UV samples far away from the center a larger weight than the ones close to the center. And there are different weighting schemes that have been worked out that allow us to control how much the different baselines contribute to the image. And we can change certain properties of the image using the different weighting schemes. So here are some examples of common popular weighting schemes. The simplest one of those is called the natural weighting scheme, and it just means giving a constant weight to all visibilities. They all count the same. Then there's a uniform weighting scheme, which means that you weight them inversely proportional to the sampling density function. What this means is that if you have a lot of UV samples close together on the UV plane, then you make them count less. And if you have a sample that's all off on its own somewhere, where there's not a lot of other samples around it, you make it count more. And that way you kind of make the sampling uniform across space. So you don't you don't prefer the area of UV space that's heavily sampled. You can also do a robust weighting, which is kind of a tunable combination of natural and uniform weighting. So you have a robustness parameter, and you can set it so that it's more natural or more uniform, and you can kind of tune it to get the result that you want. Then there's also a tapering weighting scheme, which means that you weight the visibilities by a Gaussian. So the short baselines close to the UV center get a high weight, and then the weight get lower as you move out away. So you benefit or you prioritize the short baselines. So this is an example of images that you get using these different weighting schemes. You can see in each for each of these there are numbers at the side. The top one is the resolution of the image, so the size of a single pixel. And the bottom one, the sigma, is the variability, the variance in the image. If you have a high variance, a high dynamic range, then you are able to discern fainter details in the image. So the higher the sigma, the more sensitive the image is to small details, to faint details. And so you can see in each of these different weighting schemes, they kind of produce quite different image in the end, and each one has a different combination of resolution and sensitivity. So choosing your weighting scheme is very much about a compromise between different properties of your image. Do you prioritize resolution or do you prioritize sensitivity? And there's no perfect answer that's ideal in all cases. You have to use the one that suits your science case. So this is a table that shows which weighting schemes give you better properties. So if you want a high resolution in your image, you want to see very fine details, then you can use a robust or uniform weighting scheme. But then you get pretty low sensitivity to point sources and extended sources. So if you have an extended source, probably you don't want to use a uniform weighting. If you want to maximize your sensitivity to a point source, then a natural weighting scheme is a good way to go. And meanwhile, if you have an extended source, you're looking at a big galaxy or something, then a tapered weighting scheme is probably going to be better for you, but you lose some resolution in the process. So all of these parameters are all tunable, and you have to, I think, play around with which weighting schemes give you what you want. So that's why I always say imaging is in a lot of ways more of an art form than a science. You have to kind of develop an intuition for which parameters, which tunable weighting schemes and other parameters are going to give you the image that you want. Right. So once we have this dirty image, we can then clean it by deconvolving it with the dirty beam or the PSF. So these images at the bottom show dirty beam, and then the cleaned image. Sorry, this is the dirty image, and then the cleaned image on the right, which is what you get by deconvolving the dirty beam. But because you always have incomplete UV sampling and there's always noise, it's always an imperfect process. So we can never get an exact reproduction of the sky. We can only get imperfect reproductions that we can make better or worse. So it's always a matter of trying to get the best possible image, but it will never be an exact copy of the sky. Now, to do the cleaning, we typically use deconvolution algorithms that try to accurately model the sky brightness distribution through an iterative fitting process. I'll show you what this looks like in a bit. But whichever algorithm that you use, the output is still only a model. We will never produce a 100% accurate picture of the sky because we're using a model of the sky in doing this cleaning. So here is a list of some common popular deconvolution algorithms. The popular one, or the big one that I think most people will know, is the clean algorithm, which has been used for years now. It's a very simple algorithm. It basically assumes that the sky is made up of a sum of delta functions or point sources. And then there are modifications of the clean algorithm that use a different sky model. So you can use the multi-scale clean, which instead of using delta functions, assumes that the sky model is made up of a linear combination of components of different shapes and sizes. Or you can use an adaptive scale pixel clean, which instead of using delta functions, use best fit Gaussian functions that you can choose to shape to pick out which elements of the image you want to accentuate. And then there's also a maximum entropy method, which I think is a more recent one, in which you assume a smooth sky model. So to illustrate this, let me show you what the classic clean algorithm looks like. So this has been in use since 1974, developed by this Swedish guy whose name I'm not going to try to pronounce. And it assumes that your source is made up of a sum of potentially many delta functions. So if you have a point source, then this is going to model the sky very well because it only needs one delta function or a small number of delta functions. But if you have sorry about that. If you have an extended source, then it's going to be quite difficult to model it using a bunch of delta functions. But the benefit of this algorithm is that it's very simple to implement and it works great for point sources, much less well for extended emission though. So this is the basic algorithm. We start with an observed dirty image and a dirty beam, and then we search for the location of the peak amplitude in the dirty image. And we add a delta function of this peak to the location of the model, and then we subtract the contribution of this component from the dirty image, and then we go back to step 2 to search for another peak and subtract the peaks iteratively until we reach a stopping criterion, which usually means until the image stops changing very much, until it stops helping. So this is an example. On the top left is the sky model. And you can see that the sky model is made up of a bunch of point sources. It looks like a bunch of points that you put close together to try to recreate the image. And then when you take the residual, which means the image minus this model, then you get residuals like this. And you can see that the residuals are non-uniform. They're not equal across the plane. And in fact, you can see that the residuals actually have the same shape as the image on the top right. And what this means is that because the sky model is imperfect, because it's trying to use point sources for an extended structure, we lose flux at these large scales. And that's why the image that you get out is blurry. Now, this is an example for the same image using the adaptive scale pixel clean algorithm. So this one was developed by Bhatnagar and Cornwell in 2004. And instead of delta functions, it uses a sum of Gaussian functions. And you can scale these Gaussian functions to better model extended and point source emissions. So you can use some Gaussians that are very narrow to model the point sources and some Gaussians that are very wide to model the extended emission. And you can see immediately in the cleaned image that you get much better detailed in the cleaned image. And here you can see the model on the top left that you construct matches much more closely the actual image compared to when you use delta functions. And so when you get the residuals, when you subtract those two, it's a uniform residuals, which means that you aren't losing flux anywhere on the image. So this shows that this ASP clean algorithm is much better suited to these extended structures. Right, so here's an example of some residuals using different clean algorithms. And the numbers at the top show how many iterations it took to converge on a solution or on a final cleaned image. And you can see in each of these residuals, the residuals are kind of distributed differently. And this means that the different clean methods are going to give you different images that are perhaps more suited to specific science cases. So again, this is uh, another element where making images is kind of an art form, because you have to know, oh, I want this kind of output, I have this kind of science in mind, and therefore this kind of cleaning algorithm is going to give me a better result in the end. And it's all about how that algorithm models the source brightness distribution. Yeah. So oftentimes in your own imaging, you just kind of had to play around with different cleaning algorithms and see which ones work best. And of course, the integration time for each one, the time that it takes to make the image is also going to be different. So sometimes it's also a matter of compromise between getting an imperfectly cleaned image versus one that's going to take forever to converge on a final cleaned image. Right. So let's talk about a complicating factor in all of this. So up to now, we have assumed a monochromatic signal, right? So we have assumed that we measure visibilities using only a single frequency. In reality, of course, we are observing over a wide bandwidth across a range of frequencies. And to account for that, we can divide the band into narrower channels and then measure the visibilities in each one separately. And if you don't account for these variations, if you don't do this division into channels, then there can be what's called bandwidth smearing in the image. And that gets worse at higher frequencies. So if you look at the images at the bottom, at low frequency, if you use channels which are 2 megahertz across, so you use very fine channels, you get very neat point sources. But if you use broader channels, then the point sources start to get smeared out and you get all sorts of weird artifacts around the edges. And this smearing gets worse the further away you get from the center of the image. And if you use very wide channels, in this case 1 gigahertz channel, then you get a lot of smearing. So you have to choose how many channels you're going to divide the bandwidth into, and it's a compromise between reducing the smearing, but also an increase in processing time. The more channels you have to do the imaging in, the longer it's going to take. So there's a downside to the multi-frequency effect, but there's also a positive to it, which is that we can use what's called multi-frequency synthesis to increase the UV coverage and improve the image fidelity. So for example, these are some UV coverage tracks using BLA. On the left, using only a single frequency, and then on the right, using multiple frequencies. So each color here represents a UV sample using a different channel, frequency channel. And remember, when we define the UV coordinates, we take the projection of the baseline divided by the wavelength, meaning that if you use different wavelengths, different frequencies, they move in the UV space. And that's why you get a greater coverage in the UV plane when you incorporate multiple frequencies. You can also see here the red color represents the the lower frequencies, and the violet represents the higher frequencies. And at the higher frequencies, because they have such short wavelengths, they sample the UV plane up to very high, or so up to very far away from the center, and and these set the resolution of the image. So if you observe up to higher frequencies, you get UV samples further away from the center, and you get a higher resolution image. So you can also improve the resolution of your image by incorporating these higher frequency visibilities. So this is an example of an image produced using different numbers of frequency channels. On the top left, this number of terms equals 1, meaning there's only a single frequency channel. And you can see, and then there's 2 channels and 3 channels and 4 channels. And in each case, because we're sampling more of the UV plane, it gets rid of a lot of these artifacts around the image, and we get a greater dynamic range, or greater sensitivity. You go from 9 millijansky using one frequency down to 0.14 millijansky using 4 channels. And the more channels that you use, the more accurate, or the more sensitive the image is going to get. But we have to consider the visibilities of a wide band, but we also have to consider the fact that we are working across a wide field on the sky. So in the simplest case, we usually assume that the sky is a flat plane, and that the telescope properties are the same everywhere on that plane. And this is a fine assumption to make over a small field of view if you're only looking at a small area of the sky. But the larger that area gets, the more that assumption fails. And then the more artifacts you get, especially far away from the center of the image towards the edges, where that assumption is less and less true. And this is especially important in the era of interferometers, which have very large fields of view, like Meerkat is a 1 square degree field of view, and these wide field effects can be very, very important in your image. So 2 of the major effects that can cause problems when we are observing a wide field is the primary beam effect and what's called the W term effects. So let's talk about the primary beam correction first. So if you remember, the primary beam is the response of a single antenna in the array. So you have the beam pattern of the telescope as a whole, which is the dirty beam, and then you have the response of a single antenna in the array. And this primary beam determines or can be thought of as the sensitivity of an instrument as a function of direction. So you can only see stuff with the telescope where the primary beam is strong. And the primary beam usually has an approximately Gaussian shape. So it is sensitive at the center and then it falls off towards the edges. So if you make an image, then that primary beam is going to cause the sources on the edge of the image to be less sensitive. Luckily, you can correct for this variation in sensitivity by dividing the image by a model of the primary beam. And the Meerkat primary beam and most telescopes' primary beam is well known using measurements, using a holographic techniques. They physically measure what the response of the telescope looks like using some special techniques. And on the right is an animated a depiction of the primary beam. This is at L band for Meerkat. And it's different. You can see that it's changing as a function of frequency. So the frequency is increasing here. And it also is different for polarization channels. So the top left is Stokes I, the total intensity, and Stokes Q, U, and V. So depending on the polarization channel that you're making the image with, and depending on the frequencies that you're using, you have to change the model for the primary beam in order to correct for it. But this correction is usually built into any imaging software that you're going to use. So it's well taken account for. Another important effect is what we call the W term effect, and that's caused by non-coplanarity of the sky. So that sounds complicated, but really what it means is that when we usually define the UV coordinates, we assume that the sky is a flat surface, right? Meaning that the coordinates, the UV coordinates, are coplanar. They're in the same plane on the sky. However, due to the curvature of the Earth, we should really be thinking about a dome above the sky that's varying with height. And so if we want to be precise, and if we are observing over a wide field, it becomes more important. So we need to include a third coordinate, which is the W coordinate. You can see on the bottom right here, which is perpendicular to the UV plane and going into the sky. And when we include this W dimension, then the visibility equation changes. Then we have to include in the exponential, we have to include a factor for the W, and we have to divide by the square root of the 1 minus L squared minus M squared. So it can be included in the visibility equation, but even this equation is only valid over a very small field of view. When you have a large angle, then you get 3D distortion effects, which can be very significant in your image. So one of the solutions that people use to solve for these 3D effects is called faceting. And that means that you break the sky dome into a series of small flat planes. So you break it up into flat planes, and on each of these facets, the flat facet, the two-dimensional approximation can hold, and you image it as usual using the 2D approximation, and then at the end you stitch all of those facets together. However, there can still be artifacts on the seams of those facets where you put them together. But if you use very small facets, then those effects are going to be much less, but it's going to take a lot longer to do the imaging because you have to do it individually for all of those facets. So this is an example of an image of the sky. Use it without doing three-dimensional corrections, and you can see here the size of this image is very large. It's about 3 degrees by 3 degrees in size. So it's a large image, and towards the edges of this image, there are very noticeable artifacts. These tracks in the image, and these are caused by these 3D projection effects. And then if we include those 3D corrections, then suddenly you get a lot of resolved sources, especially towards the edges of the image. So when we're using images of a large portion of the sky, which is true for Meerkat, you always have to be sure to make these 3D corrections using faceting, or there are other algorithms to take care of this as well. Right. So so that's how we get the basic picture of how we get an image. We can also improve the image by doing calibration. Calibration means correcting the amplitude and the phase of visibilities to account for effects that reduce the quality of the image. So there are effects that we know about, and we can change the amplitude and phase of the visibilities to correct for those effects. And some of these effects that we can correct for by changing the amplitudes and phases of the visibilities are the fact that you have an imperfect telescope. So the receiver adds noise to the measurements. And there can also be imperfections on the surface of the dish that can affect things significantly. Then there's also errors that come from transmitting the signal from one part of the receiver system to the next. For example, you have to digitize the signal, turn it from an analog signal to a digital one, and you have to do frequency down conversion, as I explained in, I think, the third or fourth lecture in the series. And each of those conversions can have errors associated with it that will be present in your image. There can also be hardware or software errors. No hardware nor software is perfect, so there's always going to be little bugs that you can correct for in the end. There's also observer error. For example, if you have the wrong source coordinates when you're pointing at the wrong source position, then you can correct for that after the fact. And then also atmospheric effects like bad weather and RFI, radio frequency interference. They also cause problems in your image. And then there can be contamination from other sources, from the side lobes of the telescopes that can be introduced to your image, but you can correct for those using calibration. So broadly speaking, there are three types of calibration that we can distinguish. The first is called cross-calibration, or also nowadays we call this first generation calibration, or 1GC. And what this means is that you calibrate quantities by observing a nearby source with known properties, and then you obtain a calibration solution from your observation of that source, and then you transfer the calibration solution to your source observation. So you set certain quantities to apply to your source, and that improves the result. Then secondly, there's also self-calibration, or 2GC, and that means calibrating the image using the single target field. So you don't do a second observation, you use a single target field to calibrate the image. And this typically takes place as an iterative process where you have a constantly updated sky model. I'll show you some examples of how that works in a second. But using this kind of self-calibration techniques, you can get rid of effects that are unique to the target field. So maybe there are effects that don't apply to a calibrator source, but that are present nonetheless in your target field, and you can get rid of them. And then thirdly, there's also direction-dependent calibration, or 3GC, which is a more recent development in imaging. And this allows you to remove effects that are direction dependent or non-uniform across the field. So because with calibration we apply a single calibration solution across the entire field, if you have an effect that is non-uniform across the field, that only affects certain parts of the field, you can't get rid of it using 1GC or 2GC. And you have to use some special techniques, which we all call 3GC. So let's talk about cross calibration first. To talk about that, we have to define what's called the fundamental calibration equation. And what that says is that the visibilities that we measure, Vij, is the true visibilities of the source multiplied by some factor G, which is also uh, for each combination of antennas. So here I and J is a combination of antennas, right? And for each combination, there's going to be a factor G, which changes the visibilities. So this factor G, which we sometimes call the gain solution, is a general operator that encompasses multiple effects, including effects related to the atmosphere, antennas, receivers, and correlator that could alter the phases and amplitudes. So it encompasses any effect that could change the visibilities. And we can determine this G solution to invert the equation then, and then get back to the true visibility. So we observe a source with known true visibilities, use that to measure the G solution, and then use that G solution, transfer it to our observation of the source that we are interested in, and use that to get back to the true visibilities of our source. So we can decompose this G into the gain solution for antenna element I, which is a function of frequency and time, multiplied by the complex conjugate of the gain solution for antenna J, which is also a function of frequency and time. And then the typical recipe for a 1GC calibration is that we measure the visibilities for a source with known true visibilities, and then we apply a least squares optimization test to get the solution for the G value for all antennas. You have to get a calibration solution for every single antenna. And of course, the more antennas that we have, the more baselines that each antenna is involved with, the more able we are to get a good solution for the gain solution for each antenna. So antennas with more elements are easier to calibrate for using 1GC. So we get the solution for G for all antennas, and then we observe our source. We then use those G values from the calibrator to retrieve the true visibilities, which we then use to make the dirty beam. We have to remember that G is time dependent, so and it can change quickly. So we have to repeat the calibration observations periodically to keep the solution up to date. And the better the G solution, the better the images that we're going to get out. So this G factor encompasses different effects, and you can calibrate for different quantities using this, right? So you can do flux calibration, which means that you calibrate for the true flux of sources in the field. So you measure the flux for a known source with a known flux, and then you can use that to scale the fluxes that you measure for your source. So you can make sure that the fluxes actually make sense physically. And then you can do bandpass calibration, which means that you correct the errors in the visibilities that are a function of frequency. And I'll show you some of that in a second. And then you can do delay calibration, which fixes the errors in the phase, which are present in the phase. And then you can do gain calibration, which means to determine the complex gain of each antenna. So that's we discussed gain in, I think, the second or third lecture in the series. If you need a refresher, you can go back to those. So in theory, all of these calibrations can all be done using the same source. You can observe a single source, but the gain calibration must be done using a calibrator close to the source, because the gain changes so quickly. You have to use a calibrator, typically a calibrator close to the source. So usually there's no suitable source calibrator close to the source. So you have to use a separate gain calibrator. And a typical observation plan looks like below. So you do a band pass calibration observation, and this actually includes flux calibration and delay calibration. And then you do a separate gain calibration observation. The source has to be close to your target. Then you move on to the target for a bit, repeat the gain calibration, go back to your target. These can be different targets, of course. Do the gain, get the target, and then do a bandpass calibration again. So you do the gain calibration much more frequently than the other kinds of calibrations, just because the gain changes so rapidly. And for any science case, there's going to be an optimal way to structure your observations to get the best possible calibrations. So a calibration plan for a point source like a pulsar is going to be different from a calibration plan for an extended source. Right. After we've done the 1GC calibration, the cross calibration, we can also do self-calibration. After 1GC, we should already be able to make a decent image of the sky, but oftentimes we can improve the dynamic range of that image further by calibrating the visibilities using the target field itself. So you don't observe another calibrator source, you just use the target field as it is. And you can do this using an iterative process in which we switch between the image domain and the visibility domain constantly. And in the image domain, we do the deconvolution and source finding. And in the visibility domain, we do calibration. So let me show you a diagram of how the self-calibration works. We start here at the top left. We start with an initial sky model, which we can use the 1GC image, or you can even just use a point source as an initial sky model. Then you do a Fourier transform of this, which gives you the visibilities of that model. And then you use these model visibilities to correct the observed visibility. So you get the G solution from these and apply it to the observed visibilities to get the corrected visibilities down here, right? So we're still in the visibility domain. Then we move to the image domain by doing an inverse Fourier transform. This gives us back a dirty image. And then we can deconvolve this image to get a deconvolved image. We deconvolve it from the dirty beam, and then we get a deconvolved image in which we do source finding. So you search for a source within the image, and then using that source that you have found, you construct a new, more accurate model. So you improve the model, and then you go back using this new model back to here, do the Fourier transform again, correct the visibilities, inverse Fourier transform, deconvolution, in a loop like that, iteratively, until you reach some stopping criterion, which basically means until the image stops improving. So you can do this for as long as you like, but you stop as long whenever it's not helping anymore. So here's an example of an image that you get using cross calibration, and you can see in this one there are these circular artifacts present in the image, and that's a typical signature of errors that are arising as a result of imperfect calibration. And then we can get rid of those effects by doing self-calibration. Sorry. So we do one step of self-calibration, and you can see already it's looking much better. And the more steps that we do, the less prominent those artifacts get, and in the end we get a much better image using self-calibration. But you have to be mindful of the fact that we can only correct errors in the image that arise from imperfect calibration. You cannot correct errors that come from incomplete visibility sampling. So not all artifacts in your image can be solved by using self-calibration. You have to kind of learn to recognize which artifacts come from imperfect calibration, and then those ones you can do self-calibration. And if you don't have those artifacts that come from poor calibration, oftentimes you're just wasting your time trying to do self-calibration. So self-calibration isn't always necessary. You only have to do it when you can observe these artifacts in your image. And then there's a third kind of calibration that you can do, which is called direction-dependent calibration with 3GC. And this comes from the fact that in 1GC and 2GC, we apply a constant gain solution across the whole image. So the whole image gets the same calibration solution, right? Meaning that if you have any artifacts that are present only in specific areas of the image, then you don't correct for them. You only correct for effects that are constant across the image. These artifacts can appear in the image because of these direction-dependent effects, especially further away from the image center. And these effects include the beam shape effect. So that includes the primary beam correction that I spoke about before. It can also include errors in the pointing. Remember, the telescope pointing itself is often imperfect. It has an error associated with it. You don't know exactly precisely where you're pointing. And that error can introduce a direction-dependent error into your visibilities. And then there's also ionospheric and tropospheric variations, which are direction-dependent and can mess with your visibilities. 3GC fixes these errors by using a differential, meaning a spatially varying gain solution. So you, instead of applying a single gain solution to the whole field, you have one that is dependent on the direction. And that means that you can improve the dynamic range of the image, especially over a wide field of view where these 3D effects become very important. So I'm not going to go into the maths of it. It gets pretty complicated with Jones matrices and things like that. But if you are very interested, there's lots of good resources to delve into this. I'll just show you an example of an image of some patch of sky. If you don't do any differential gains on the top, the inset, sorry, on the bottom, if you don't do the differential gains, you see these artifact patterns around the point sources far away from the center of the image. But when you do apply these differential gains, the point sources get resolved much more satisfyingly. So in the wide field domain that we are in currently with Meerkat and so on, these 3GC calibrations are very important, especially if you're observing a source that covers a large part of the sky. And there are various different schemes that implement corrections for these 3GC effects in software. You might be familiar with DD facet, for instance, is one of these 3GC calibration steps. Right. So that's a very surface level overview of this topic. Let me just give you some summary of everything that we've done. So when we take the Fourier transform of an incomplete UV coverage, we get a dirty image, right? With lots of artifacts because there's missing information in the UV plane. We can apply different weights to those visibilities to alter the output image in terms of the resolution and the sensitivity at various scales. And then we can clean this image by iteratively deconvolving the dirty beam, which means the response of the interferometer from the image. But we also have to account for some complicated wide band and wide field effects. There are thousands of effects that you can correct for if you want to. But we can do cross calibration. We can do calibration to get rid of some of these effects. We can do cross calibration with a known source that helps us to set some important quantities for the observation that we need to make the image. We can do self calibration on a single field that removes artifacts specific to the observed field. And we can do 3GC, which is direction-dependent calibration, which corrects for some effects that are not uniform across the field. So that's it for me. Any questions? I think there are some in the chat. Okay. So Rahul asks, why are Fourier transforms computationally expensive? So a single Fourier transform for a single value is not really computationally expensive, right? The problem comes when you try to do a Fourier transform for every point in a UV plane. You have lots of points, and the time it takes to do each of those Fourier calculations to calculate that integral scales as a square with the number of those calculations that you have to do. And so you can imagine if the number of UV points increases, you have more and more baselines. Very quickly, a single Fourier transform can take a very long time. And as we've seen, you have to do that for each frequency channel for multiple polarizations. It just becomes unfeasible to wait that long. And so we do fast Fourier transform, which optimizes that process by making the scaling of how long it takes to be n log n instead of n squared. Does that make sense, Rahul? So when we're talking about computationally expensive, what I mean is how long does it take to do an operation? And of course, time is money when you're using computation resources, so it can be literally expensive as well. Does that answer your question, Rahul?
Yes, sir. And I just
Cool.
want to know, like, how are fast Fourier transforms cost effective? Do they use an iteration? Do they use a loop?
Yeah, so fast Fourier transforms use an iterative algorithm to do the Fourier transform. I'm not exactly sure how that works, but one of the main features of it is that it uses a grid of a grid of values to do the Fourier transform instead of using the values at continuous points. So it simplifies the process by snapping those values onto a grid, and then it has some very clever algorithms that does the Fourier transform very quickly. There's lots you can read up on about fast Fourier transforms.
Okay,
Okay,
so and what are grid of values?
sorry, say that again.
So what are a grid of values?
So we're talking about the UV plane here, right? So we have visibilities as a function of U and V. So each U and V pair, we have a value of visibility. And then we have to use a Fourier transform to transform all of those values into pixels on the image. Does that make sense?
Yes, it does. Thank you so much, sir.
And then Jeffar asks, what is the main cause for dirty images and why is the Fourier transform computation expensive? I've already said why it's expensive, because you have to do it for lots and lots of points on the UV plane. And then why are there what is the main cause for dirty images? The images are dirty because we don't have perfect coverage of the UV plane. So if I can go back all the way to the start here. So this relationship between between the image of the sky and visibilities is only valid perfectly when we have a value of the visibility for every single combination of U and V. And there's infinite combinations of U and V, right? But in reality, we have a finite number of baselines, and each one of them gives us only one complex value for one combination of U and V. So we have some values on the visibility plane, but there's lots of gaps between them. And when we do the Fourier transform, because of those gaps, there's missing information from the visibilities. And then when you do the Fourier transform, it kind of it fills in those gaps, and it can fill it in with all sorts of garbage. And that's why you get these artifacts on the dirty image. Does that answer your question, Jeffar? Okay. Yeah, Kevin posted a nice video about the fast Fourier transform. It's very helpful. It's a very widely used algorithm in all sorts of different applications. I think Popnon, you have your hand up.
Yes, please. Okay, thank you for the presentation. I have a question. My question is based on the self-calibration.
Yeah.
Once you're done doing the bandpass calibration and the gain calibration, and you want to look at your target, maybe looking at the spectrum windows, all the spectrum windows, plotting the amplitude versus the channels.
Yeah.
And for your target source, and you notice that there are some wiggles. The target source which contains both your line and your continuum emission, and you notice some spectrum windows has some wiggles on top. What can be the cause of that, and how can it be removed?
So you're seeing wiggles or sort of artifacts in the image after you've done the self-calibration.
Yes.
Yeah, that could be any number of things. Is it visible across the entire field?
Yes, across the entire field.
Okay. So that would indicate that it could be a matter of imperfect 1GC, right? Because the gain solution that you get from the calibrator sources are always going to have some assumptions in them, and there might be some effect that you're not accounting for in that gains in the calibration solution. But to be honest, I'm not familiar enough with the software and all these things to give you advice about exactly what effects you can look for. Yeah, my advice would be to ask somebody who has some experience with these things. Oftentimes they're very clever at kind of recognizing different signatures that correspond to a specific effect that you haven't accounted for. So yeah, sorry, I'm not. I don't have the knowledge of the specifics to really help you on that.
It's fine. Thank you.
Okay. Any other questions? Comments?
Hi, sir. I have another question on the chat.
Yes. Oh, on the chat. What is it? Why is an inverse FFT used to obtain a dirty image of corrected visibilities instead of the Fourier transform? So that's just so Fourier transform is directional, right? If you want to go from visibilities to the intensity, you do the inverse Fourier, and when you go from the image to the visibilities, you do the Fourier transform. It's just yeah, the directionality of that transform. Yeah, you can read up some more about Fourier transforms if you are still confused about why you need a Fourier transform in one direction and the inverse in the other direction. It is basically going from a when you go from a time to a frequency domain, you have to use the inverse to go the opposite direction. Yeah, I hope that makes some sense, but I would advise you to maybe brush up on the Fourier transform itself. I think the video that Kevin has posted should be useful for that.
Okay, sir. Thank you so much, sir.
Cool. Anything else? And
Sorry.
yes, go ahead.
Yeah, I would like to ask something, but first of all, thank you for this great lecture. My question is regarding self-cal. I would
Yeah.
like to know if self-cal is the same as cleaning, because I remember that one day I was watching a video and then they said they were only talking about cleaning process, which basically removes artifacts on the image that we are getting. But then there is other thing that is called overclean, which means that when we clean an image, we can do it multiple times. And if you do it, oof, if you do it many times, your image can get overcleaned. So I would like to know if self-cal is the same as cleaning, and if there is a specific times of cleaning that we can do it to avoid overcleaning.
Yeah. Okay. So the first thing, the difference between cleaning and self-calibration. So cleaning is the broad term that we use for the deconvolution process. So you have the dirty image, which is the Fourier transform of the UV samples, and that is a convolution of the clean image with the dirty beam, and the removal of the dirty beam, that is cleaning. And this can be an iterative process, as I showed with the clean algorithm, to iteratively remove that dirty image. 2GC specifically is about 2GC is about improving on this image using calibrations in the field itself. So when you do the Fourier transform, instead of doing the deconvolution once, which is the cleaning process, you do it an iterative or in a continuous loop, right? So the 2GC process involves a number of cleaning steps. The cleaning is the deconvolution, and this 2GC calibration involves the cleaning as one of its steps. But it's a more complicated process because it's this repeating iterative process where you improve slowly a sky model until it matches the sky. Does that clarify the difference there for you?
Yes, thank you very much.
Cool. I think there might have been another part of the question, but I can't remember it now.
Now I got it.
Okay. I think you said something about over cleaning. And again, I'm not an expert on this, but I think over cleaning refers to if you apply this cleaning loop too many times until you start removing real objects in your image accidentally. So you can do this too many iterations until you just obliterate any real objects that are in your sources in your field as well.
All right.
I believe that's what they're referring to.
Okay, thank you.
Cool. Okay, let's see. Mark says, hi, how to access your videos. Hi, Mark. Thanks for joining us. So the videos for each of these lectures get posted onto YouTube at the end of each lecture. I send it out to the same mailing list that I sent this out to, so I'll upload this today, and you should get the link wherever you got this.
Okay, thank you.
Cool. And yeah, and I send the slides out as well. So yeah. Okay. I think that's it. Again, I'll just remind you, we have some really good experts in the group who are very experienced with imaging. So I encourage you to reach out to them if you have any specific questions. The whole labyrinth of software and different calibration techniques and everything, it gets very complicated very fast. So yeah, we have lots of good people in the group. Make use of them. And yeah, thank you all. Very welcome. And I'll see you again probably in 2 weeks' time. I think we're going to start talking more about my specific area of expertise, which is transients and that kind of thing. So looking forward to that.
Okay, sorry.
Okay.
Another question. Can I
Yes,
be
yes.
added to the mailing list? Because I think I got this from people sharing it, so I'm not sure that what you send out.
Okay. So there's a mailing list for the Unisa Astro group. I think is it Willis who's
I think with Prof. Shibweze, right?
yes.
Okay. I think I belong to this list. Okay, thank you. Yeah.
Okay. Yeah, if not, I'll put my email in the chat as well. So if you don't get it, you can send me an email and I'll send you a link directly.
Okay. Good. Thank you.
Cool. Okay, cool. Yes, have a nice day, everybody. See you again later. Bye-bye.
Hey, bye.
Bye.
Yeah, thanks very much.
100%.
Appreciate it,
Have a
Willis.
nice day.